All right, so I'm going to give a little bit of a tour of generalized function theory and transcribing distributions in the limit order book. So the limit order book is never really going to have a smooth density. Let's say we want, to describe the density of the state of all these this tick data, right? It's going to be populated by finite volumes, all right? So let's say we have n, agents with some positive, volume that's posted at some level, at some price level. And we're just going to describe it as the sum of Dirac measures, right? It's going to be, they're finite volumes, and mathematically a sum of finite Dirac measures. That's your density, all right? And this object is not a classical function, okay? It is a continuous linear functional on a space of smooth test functions with compact support, all right? In other words, just a bunch of Dirac deltas, all right? And to pass this from singular, this is a singular, microstructural statement about what's happening in the order book. And we want to pass this to macroscopic latent volatility field that we discussed earlier, right? We want a liquidity. I'm sorry, not volatility. We want a liquidity field that enters, with the hydrodynamic equation. Let's, for good measure, let's write it out again. So we borrowed it from Leonard Lifshitz, volume 6, which is that this field would actually describe an actual fluid, as this diffusive type parabolic term minus the relaxation of this field, right? Because as you start, draining liquidity from it, it's going to relax and fill back in and replenish the liquidity. Some indicative eigenfunction here that gives us a sine of our variable itself plus a white noise tensor. And this Gaussian white noise stress tensor is going to obey a second moment relation given by the fluctuation dissipation theorem, which says that if I were to take the covariance of these, Gaussian measures, of these Gaussian space-time white noises, this should give me, the 2 times the Boltzmann constant times the temperature, in this case, the temperature of the market, times eta, our viscosity or dissipative term, times the product of these two distributions here, and supported over space and time, right? Compactly supported over space and time. And remember, this functional, or this part here, represents the linear relaxation, and the noise term gives us what? This allows us to describe the stochastic arrivals and cancellations that keep the book alive. But because the noise covariance is tied to the same, it's restricted by this Boltzmann constant. Again, we talked about this last time. That appeared really in just the idea of maximizing entropy. Microscopic volatility, again, comes from integrating everything. So this was how we described or bounded microscopic volatility in terms of the temperature of the market over the viscosity, of the fluid. Okay, now that we reviewed that, if we were to follow the work of Gelfand, Gelfand, and Shilov. I can't spell, dude. When I'm recording, I just can't spell for some reason. Don't know why. But we can introduce something called a mollifier. And what the mollifier is it has some epsilon. I'm having a bad response with my pen too. Let me tighten it a little bit. Okay. We can describe a mollifier that looks like this. And the mollifier is normalized, so that if we were to take an integral over this, this would give us a rescaled kernel, which then looks like epsilon sub epsilon of x. That would say here's our mollifier, and here's our kernel, and we're dividing it by this little epsilon here. The convolution of this mollifier, remember we have these little normalized, it's exactly what we covered in our differential equation series. Convolving this with a field, all right, would give us a regularized, if we convolve the density of this with our mollifier, this would give us a regularized field itself that allows us to, in general, in a distributional sense, as epsilon goes to 0 from the positive side, our regularized field will converge to the density itself, to the real density in this distributional sense, right? And as you can see, that's really important because for every test function that exists, in the space of compactly supported test functions, so just a bunch of generalized direct delta functions, empirically, what this would show is that the covariance of this with any chosen, this covariance of this with any field would give us the covariance precisely, or would converge to the covariance precisely of the distribution with the test functions. All right? Empirically, this mollification scale, this epsilon, we choose it so that it exceeds the typical tick size itself from the Orderbook data. All right? And we would say then that phi sub epsilon stabilizes to a linear profile that was kind of, we kind of pulled out of our butt last episode, okay? And this was used for the entropy functional, if you remember, to give us our second law type things and maximizing it. So all subsequent, operations that we did, right? Differentiation, multiplication by coefficients, Fourier transforms, all of these things. If you read this series, you can start with volume 1 and 2, and then later we're gonna use some results from 4 for the Bochner-Schwartz theorem. But as you can see, these things remain well defined. All right. They remain well defined in the distribution itself. So the regularization step that we do here to regularize the field, in a sense, it's just a mathematical transcription that allows us to the discrete Orderbook deltas to enter a continuous fluctuating hydrodynamics without loss of information. All right, so that's very powerful, the theory of generalized functions. You can see why we would be concerned with, necessitating this mathematics. And in the many-body limit, then, right? If we were to take the number of active orders, in to go to infinity, what would happen? Well, the space of test functions, test functions here, will upgrade to something we call nuclear spaces. And nuclear spaces, denoted as, some S, because everything's, entropy's S, what else is S? Action is S. Everything we use S, whatever. We're also going to use it for nuclear spaces. And basically, you can think of these as like countably Hilbert spaces. They're countably Hilbert. And they have these two properties, or one of these two properties are probably the most important, which would be that they rapidly decay. At infinity. I'm sorry, my thing is being so laggy. Jesus. And they have something called Gevry type growth. Of derivatives, all right, which gives us some structurally preserving properties within the space. And these spaces here are called, these nuclear spaces give us this class of spaces called Montel spaces. Right? And Montel spaces, in more of an abstract kind of like mathematical definition that's not really clear about what it does specifically, it just says that every bounded set is relatively compact. Okay, relatively compact in the weak star topology. What that basically means is that if we had a family, let's say we have a family of these, or let's take the set of all these regularized fields, okay? And this family is indexed by the regularization parameter here. And it forms a bounded set in the nuclear topology, okay? Then, by Montel's theorem, there exists weakly convergent subsequences that they weakly converge to the limit of phi itself as the macroscopic, latent. Oh my god, bro. As the macroscopic latent liquidity field. And the nuclearity, right? The nuclearity of this space, which just says rapid decay and Gevry type growth of derivatives, it guarantees continuous dependence of all observables. So these things do depend on all the observables, the kappa, everything that we can extrapolate from the order book. The entropy, variance, impact, the impact scaling, all of these things. On the microscopic data, this should supply thermodynamic limit compactness needed to extract the macroscopic laws from microscopic order flow. Right? So that's kind of a lot, and that was more conceptual than anything. But I just wanted to give some motivation as to why you might want to, or just convince yourself that you need to open up Guilford and Shilov's generalized function series, okay? Because, and just putting it into the context of the application of how I'm going to actually use this in practice, okay? And compute things, all right? So, now, there's a really good quant video, or there's a really good video on Hawk's processes, so I'm not going to get super into it, but order arrivals, right? They're usually modeled with something that we call a Hawk's process. And shout out Quant Guild. Okay. He has a video on the Hawk's process and goes through very well. So I'm not going to repeat any information that's really out there on the internet already. Because I just don't really want to waste your time. But a market order, really, what it does, the logic of it is if you place a market order, right, it's going to trigger new limit orders or cancellations with some intensity that's governed by a power law, all right? Pretty conceptually straightforward. But this power law kernel can have a branching ratio in, where, you would, this is basically, you can think of this as the expected number of offspring per event. So if I place an order, what is the expected number of the offspring per the event? All right. And empirically, it's usually measured to lie arbitrarily close to the critical value of n equals 1 itself. And it turns out for Hawk processes, when you approach 1 from the right, the process will become critical, and avalanche sizes obey power law statistics, and the classical variance of volume imbalance will diverge. Okay, and the covariance of the noise here, the covariance of the standard classical statistical description of this variance, it'll diverge. All right, and it lives outside of the space of ordinary functions. In other words, it's not in the space of ordinary functions when the branching process starts to do this thing. All right, and so to define the corresponding probability measure rigorously, we can invoke something which is covered in volume 4 of Bielefeld and Shilov. And again, this is all about generalized functions. There's something called the Bochner-Schwartz theorem. Again, my apologies that my my pen is being very weird and laggy, but we're doing our best. The extension, this is really the extension of Bochner's theorem to basically just nuclear spaces, okay? And how you can think about this is, let's say we have a functional, all right? Let's say we want to embed this, covariance, right, as a functional itself. All right, and this would be a continuous functional. Hold on, let's write it out real quick. This is what we want to do. Market eta in the price is supported in price. Okay, and let's say this continuous functional on the nuclear space. This would be the characteristics functional. This is said to be a characteristic functional of a unique radon probability measure on the dual of that nuclear space. All right? So for a white noise stress tensor that looks like this, the Bochner-Schwartz will guarantee the existence of a generalized. So this guarantees the existence of a generalized random field. A generalized random field whose second moment is exactly this covariance. Exactly this covariance in a general functional sense. Why is that powerful? Because even though it's kind of like the difference between Hilbert spaces and then doing math and Sobolev spaces, right? Except we're doing this for generalized functionals. So even though we can have like pointwise variance, right, which says, let's say we have pointwise variance, we take the square of, our noise. If this diverges, right, much in the sense of like having a Hilbert space that you have a point charge, and like if you take the derivative there, at that point it blows up to infinity, infinite energy, like that doesn't exist, right? It's not physical. So in a sense, we're making sure that we, it's analogous in that way. This connects exactly in the sense of if we have a diverging variance, a pointwise variance, the second moment still exactly or the Gaussian random field will have this second moment that guarantees we can still do mathematics on these spaces, right? In the sense of like, and this is not that esoteric of a thing, and this resolves a tension, the very tension of, hey, do plane waves actually exist in Hilbert spaces? They actually don't. There's no such thing as a plane wave on a Hilbert space, right? Even though we do the quantum mechanics for that all the time. No, it takes a little bit more, it takes some more thinking, okay? Because the plane wave itself like extends itself across to infinity. Like obviously, like it has to be bounded in some sense, right? And so that's what we're doing when we talk about functionals, right? And generalized functionals, positive, definite, and continuous functionals. Okay, now this also relates to the Seifert closure, right? Because we would say the exponentiation of minus the total entropy over Boltzmann's constant here. And if we set that to be equivalent to 1, that extends distributionally because entropy production remains continuous in the nuclear topology that we described here. And so we're preserving a lot of these physical structures like, this covariance in a more general sense, even though this might actually diverge, and also the dynamics of or the hydrodynamics that's happening as well in our generalized process in random field. Okay, now this allows us to mathematically have heavy-tailed liquidity fluctuations, right? Near the criticality region, near this criticality region from the Hawkes process itself, whenever it decides to blow up. And we just kind of avoid having to deal with those things in a stupid manner. So preserving the fluctuation and the dissipation, that is relation that is, related to both of these equations here, right? And the Fokker-Planck hydrodynamic operator that will arise from the coarse graining logic that we talked about in the last episode would be, let's say we have fancy calligraphic L here. The operator would turn into the parabolic PDE in space minus the linear relaxation operator here plus, like more advection type terms, whatever. But now this will, I don't know off the top of my head, but it acts on nuclear test function spaces now. Okay, so we're not just, we're promoting this general, test function itself to using nuclear test functions. Okay, and we're going to act on nuclear test function spaces, and we'll establish now that parabolic equations with this kind of diffusion coefficient will emit unique solutions in the dual spaces because of the Schwartz theorem. And so the nuclear embedding theorems will guarantee continuous dependence on initial data and instantaneous smoothing of, singularities. So any Dirac delta type, singular integrals that we would be concerned with a liquidity shock, it's regularized. We guarantee that we get a regularization, for liquidity shocks in general, that is regularized by the epsilon regularization parameter over the diffusion constant itself. All right, and this would be the time scale. Wow, it's really horrible. Scale. Oh my god, the lag is so bad. What the hell? That's horrible. Anyways, that's the time scale that where the liquidity shock is regularized up to. So, and this is mathematical. So, for singular propagators like Green's functions, for Orderbook withdrawals, they all remain well defined. Okay, it goes back to this goal here. We want to make sure that everything is well defined so that we can link the entropy functional, right, so that we can link this guy, this entropy functional that we talked about previously, to the fluctuating hydrodynamical field, or the hydrodynamical field here. All right, that has some, space-time white noise. Thus, the discrete, Orderbook deltas here, again, are transcribed into this continuous field by mollification, and this regularized field that converges to the density itself that we initially were trying to describe, and the diverging classical variance of near-critical Hawkes processes and order flow, which is most of the time, is, it's usually really close to around 1 for the branching parameter whenever you put an order. And so this allows us to then have generalized Gaussian measures by the Bochner-Schwartz theorem, and the advection diffusion operator remains uniquely solvable under singular jumps. Okay, every single one of these steps will preserve that the variance of the process is equivalent to the Boltzmann's constant over some observables, or it's related to observables in and of itself, that can be derived from whatever potential we choose for a latent liquidity field. In this case, we're choosing the very simplest one. And the noise covariance ensures that Seifert's integral fluctuation theorem, that we talked about previously as well. But yeah, macroscopic equations now we pose them as nuclear duals, okay, and belonging to nuclear dual spaces, okay, and these functional spaces. So we're now ready to talk about Stratonovich stochastic calculus while maintaining, structure and things like infinite dimensional sensitivity. So that'll be next episode. But I just kind of wanted to put this video out so that you can kind of, be thinking about generalized function theory and give people a little bit of a reason to get excited about the power of describing densities in this way. All right? Thank you.